In this lecture, we're going to talk about gauge blocks. They are a very precision gauge and need to be handled with great care in order to maintain their precision. I've created a variety of videos from the internet for both professionals and practitioners to give us an idea about some of the content of the book, but in laboratory environment. Then I will go through a variety of information left from the chapter that I think is important and you'll need to know. Let's get started.
The beautiful small city of Eskilstuna, Sweden, is famous for steel and machine tools. Near its historic main square are factories with products requiring the finest craftsmanship. Here, over 300 years ago, Sweden's tool-making had its origin. And in this ancient town, world industry was revolutionized a half-century ago by incredibly accurate products of the Johansson factory. At the foundries of Sandviken, molten metal is transmuted into the finest steel, writhing like giant serpents. At the Johansson plant, fully processed steel bars of all required dimensions move from vast storerooms to machines, cutting them into proper lengths for milling. Here, master machinists shape blocks of steel that made modern industrial science possible, for they are the world's standard engineering measure. The unbelievably precise Johansson gauge blocks. These operations may appear quite simple, but the cutting and polishing procedures demand utmost skill. The creation of perfect flat planes of steel is one of the greatest achievements of industrial science. Each gauge block must pass rigid spectroscopic tests and be completely perfect, for it is the final authority in all highly accurate measurements. This device, developed by the company's founder, detects an error of 1/25 millionths of an inch in these blocks, which check accuracy of gauges, making high-precision mass production possible. Now, engineer Johansson demonstrates an amazing property of these blocks, first ringing several together. Although non-magnetic, they adhere. He attaches top and bottom blocks to cables of the tensile strength tester, which indicates their remarkable cohesion, possibly the result of molecular attraction. The blocks cannot be forced apart, even with a tensile pull of 120 kilos or 570 pounds per square inch. Only with such amazingly fine measuring units could our modern machine age come into being. Gauge blocks in various combinations are exceedingly sensitive to temperature changes. Here, a cylindrical gauge is being tested. Now the gauge is slightly warm, with this result. This matched set may seem hardly more impressive than a box of children's blocks, but with them we have built our complex industrial world. Endless combinations provide all needed dimensions. Gauges of all types everywhere are tested with these blocks produced in a little Swedish town where half a century ago modern industrial science was born.
Hello, I'm Jim Salisbury with Mitutoyo America Corporation, and welcome to the Metrology Training Lab. In this episode, we want to discuss the truly amazing gauge block and talk about their use and a little bit about their calibration. I have to admit, I'm a bit awestruck with the gauge block. These simple little blocks are something special. Each one with their flat and parallel surfaces, and with an accuracy of just a few millionths of an inch. We've used gauge blocks in previous episodes of the Metrology Training Lab, but in this episode, we get to understand them better and appreciate their role as a premier measurement standard. Gauge blocks come in sets like these, and you can use these sets to build any length you need. And when done properly, those lengths are more accurate than pretty much anything else. What's even more amazing is that gauge blocks were invented over 100 years ago, and they haven't changed much in that time. They have quietly played an important role supporting all the incredible technologies that have been developed since the early 1900s. That's pretty cool. Gauge blocks were invented in Sweden by C.E. Johansson. He didn't invent the idea of length standards, but he patented the idea of a set of blocks that can be used to build various lengths. And he was an incredible machinist and his company was able to produce gauge blocks to tight tolerances that allowed so many others to achieve new levels of accuracy in manufacturing. Some people will refer to gauge blocks as Joe blocks in reference to Johansen. Johansen was also a pioneer in precision engineering, and the standard reference temperature of 68 degrees Fahrenheit or 20 degrees C comes in part because he needed everybody to pick a common temperature. And when the top scientists around the world asked, he recommended 68 degrees Fahrenheit because that worked well for him. We have here an actual set of Johansen blocks that one of my colleagues at Mitutoyo America collected. You can see the Johansen name and Sweden marked on the gauge blocks. The sets we sell today don't look much different. Modern gauge block sets basically follow his 100-year-old patent. During World War I, the US government became worried about the supply of gauge blocks to the United States from Sweden. Along came a Mr. W.E. Hoke, who developed his own way to make gauge blocks around 1917. He made them round with a hole in the middle to make them easier for him to lap flat. The square gauge block with the hole in the middle was derived from Hoke's design. And still today, you can buy gauge blocks in either Johansen's rectangular design or in Hoke's square design. Rectangular blocks are much more common, but some people like the square blocks. In other episodes of the Metrology Training Lab, you will see us picking either rectangular or square blocks for various tasks. For the interested viewer, Mitutoyo has published a little book on the history of gauge blocks. You can download that for free from our on-demand educational resources on our website. Modern gauge blocks come rectangular or square in inch or millimeter sizes. The typical set includes lengths up to 4 inches, but you can get long block sets up to 20 inches. And you can special order gauge blocks up to 40 inches or 1 meter long. The most common material for gauge blocks is steel, mostly because the price is quite attractive. Other standard materials include carbide and ceramics. One of the big advantages of ceramic gauge blocks is that they don't rust. However, if you take care of steel blocks, such as wearing gloves when you handle them and putting light oil on them when they're stored, they can last years, even decades, depending on how you're using them. For this episode, however, I'm going to mostly use ceramic blocks. The real reason is that these lights here are quite hot, and my hands sweat in these gloves. And getting sweat all over steel gauge blocks is not good practice. Now I could tell you some more advantages of ceramic gauge blocks, but I don't want to sound like a salesman, and that's not the purpose of this episode. Gauge blocks are sold by grades. The grades define tolerances for the flatness and parallelism of the faces, as well as the tolerance for the size that's marked on the blocks. The grades apply whether the blocks are ceramic or steel, and whether they're rectangular or square. For example, these 3 1-inch gauge blocks, if they're all grade 0, according to the tolerances in the standard, it would be plus or minus 6 millionths of an inch. If this gauge block, or all 3 of these gauge blocks, have been properly calibrated and found to be in tolerance, then I would know that the length is somewhere between the minus 6 millionths and the plus 6 millionths of an inch. I told you these things were accurate. If this was instead, say, a grade AS2 gauge block, the tolerance would go from 6 millionths of an inch up to 24 millionths of an inch. Gauge block grades are defined in national and international standards. In the US, we use the American National Standard for Gauge Blocks, ASME B89.1.9. You can also find the tolerance table in the Mitutoyo catalog. All manufacturers of gauge blocks sell them in grades in accordance to the standards. You should select gauge blocks based on your accuracy needs. In a calibration lab, grade 0 gauge blocks are quite common. So, that's a brief introduction to gauge blocks. How do we use them? Gauge block faces are very flat and very smooth. The reason for this is that allows gauge blocks to ring together. Without using any adhesive, gauge blocks can be brought together and the flat, smooth surfaces will adhere to each other without causing any damage. When done properly, the gap between the two gauge blocks is somewhere around 1/1,000,000th of an inch. And when you're done, they can be broken apart and reused over and over. And any flat or smooth surface will ring together. Steel to steel, ceramic to ceramic, even an optical flat, such as shown here. I've rung together 3 different gauge blocks: rectangular, steel, ceramic, and an optical flat. All 4 of those blocks are rung together nice and tight. That's pretty neat. The idea behind Johansson's original patent was the particular sizes in a set of gauge blocks. They allow you to build an accurate stack of gauge blocks to create any length you need. So let's walk through the ringing process. When you ring blocks, you apply quite a bit of force. To avoid scratching your blocks, it's important they are clean. It's important, particularly for steel blocks, to also make sure there is no raised edge or burr or some sort of ding. First, I'll use some denatured alcohol to clean the block. And then I'll use this Mitutoyo Cerastone to remove any burrs. This is sometimes called conditioning the block. We're not changing the length of the block, we're just removing any high spots, particularly on the edges. I can use a small Cerastone like this, using a push-pull technique, or I can use a large one like this, and some people like to go in a figure-8 pattern. And no, you don't have to buy a Mitutoyo Cerastone, but they do work well. Some people recommend using a small granite surface plate. And it's hard to say how often you need to condition your blocks. It really depends on how you're using them. If you were to very lightly slide a gauge block across a surface plate, you may feel it catch or hear kind of a scratchy sound that indicates a raised spot. In those cases, you should do the conditioning. I'm also not going to pretend to understand the physics on why ringing works. I'm an engineer. I just need to know that it works and how to do it. In fact, it seems to be a bit debated as to why it really works. We'll leave that for the interested viewer. What is important to know is that ringing works best with a very, very slight amount of light oil or grease on the gauge block faces. We really don't use anything special in our lab for ringing. We have these 20-year-old stamp pads lying around that have some WD-40 sprayed on them. Yes, WD-40. I can only imagine the comments that will be posted on our use of WD-40. All you need to do is dab the gauge block in it and then wipe it off on a dry cloth. We don't use any solvent here because we don't want to remove the oil. We want just a little bit left on it. Now I'm going to ring these 2 blocks together. And you do have to apply quite a bit of force when you're sliding one block against the other. So I'm going to set these two up here, and I'm going to try to slide this block against this block as so. This is the kind of the slide technique. Another technique is kind of the push and slide technique, where you come from a side, you go like this, and then you rotate the block as you're pushing. I'm not doing it now, I'm just trying to demonstrate how it's done. On the square blocks, you can typically use a push and twist technique. In fact, it looks like I just accidentally wrung those two together. All right, so back to these two blocks here. I'm going to push on this while I'm sliding across here, and you can see my thumb turn a little bit white as I do that. And if I did it right, those two blocks are now rung together pretty well. When you're all done using the rung gauge blocks, you can just slide them back apart like this. If you leave the blocks rung together for, say, several days or more, it can become very hard to take them apart. So don't leave them rung for too long. Ringing requires handling the gauge blocks, which may warm them up a bit. So once they're rung, you can clean the outside surfaces and then let them sit for a little while to cool back to the ambient temperature. How long to sit depends on how much you handle them and what your accuracy needs are. If you want to see how well you can ring, a fun and easy test is to ring two blocks together that add up to the value of a third. Say this 450 and 550 block, which add up to 1 inch, and we compare it to a 1-inch block. So we ring these two blocks together, and then using something like a high accuracy detector like this mu checker, I can then compare the rung block stack to the single block. Now this test is not super accurate, but it should be good enough to see if your ringing skills are good enough to, say, calibrate a micrometer. Our last topic on gauge blocks is their calibration. In our calibration lab here at Mitutoyo America, we use really cool automated gauge block comparators. But we have a manual version here in the metrology training lab. So let's head over there and I'll discuss some important topics on calibration. Gauge blocks are usually calibrated using a comparison method. This is the master block and this is the customer block to be calibrated. We set the comparator using the master block. And then measure the customer block. In accordance to B89.1.9, the length tolerance for gauge blocks applies across the entire surface of the gauge block, not just at that gauge point. And the standard discusses the importance of checking the size in addition to the gauge point at all four corners. This fixture here moves the gauge block around such that we can measure the four corners quickly and easily. In order to state conformance to grade in accordance to the ASME B89.19 standard, all 5 of these points must be in tolerance. Gauge block calibration practice in the United States is sometimes a bit sloppy. To save calibration costs, some people have been convinced to go with a single point calibration, where the corners are not checked at all. The only time that's acceptable is when you're only using the gauge block at that exact measurement point. And I think that's pretty rare. Please be careful with exposing yourself to calibration risks just to save a few dollars. If you just need a cert to show some auditor, well, that's your business. But if you really care about quality, do the calibration right. I hope you learned a few things about gauge blocks. If you have questions or want to see something else on gauge blocks, please post your comments. Thank you. I'm Jim Salisbury, and I'll see you next time from the Metrology Training Lab.
So the boss came in and said, "Hey Bailey, remember these 15 items I gave you here to grind?" And I said, "Yeah." And he said, "You had to grind them within 2/10, right?" And I said, "Yeah, I did." And I said, "I got them within 2/10. He said, "You scrapped them." I said, "What?" He said, "You scrapped them." I said, "No, I didn't. I know I got them within 2/10. I know I did." And he said, "Well, did you use a stack of gauge blocks, like several of them?" And I said, "Well, I had to because there were a number of blocks missing, so I had to make a combination up. But I know I did the math, and I know I got the right combination of blocks." He said, "Well, did you use a deviation chart?" And I said, "No." He said, "Well, if you didn't use a deviation chart, then how do you know that the blocks are accurate?" I said, "Well, they're gauge blocks." He said, "Yeah, but there's a deviation chart that shows you that they're never exactly what they say they are. They're off a few millionths here and there. And when you put a bunch of blocks together, you're going to have a deviation." And I said, "Well, no, I didn't take that into account." He said, "Well, I think that's part of your problem." He said, "These parts are undersized. What are we going to do with them?" I said, I don't know." He said, "Well, what about temperature?" And I said, "What about it?" And he said, "When you checked the part, was it back to ambient temperature?" I said, "That's a big word. What do you mean ambient?" And he said, "Room temperature." I said, "No, I mean, it was a little warm when I took it off the machine." And he said, "Well, what about the gauge blocks? Were they warm?" And I said, "Well, I had them in my hand for a while, and yeah, they were kind of warm." He said, "Well, do you realize that if the gauge blocks are warm, they're going to expand, and if your part's warm, it's going to expand, and you got a deviation problem, all that's going to add up and is going to take away your tolerance." And I said, "Really?" And he said, "Yeah, absolutely." He said, "Let me show you." So he came out, he took a temperature gun like this, and he said, "Let's take a look and see what the gauge blocks are at or what they should be." And Jim, can you see this? Okay, good. Now, let me check the temperature of the gauge block that's stabilized. Can you check that one, Jim? All right, so you can see there's a difference in the temperature. The difference in the temperature is approximately 8 or 10 degrees, I think. And that little difference, I'm going to show you the difference here. This is the correct set of gauge blocks. That's on 0. This is a set that's warm, and there was no compensation made for deviation. So you can see that's 2.5, correction, 1.5, almost 2/10. So the difference between an accurate set of gauge blocks, which is what my boss used, and the stack that I used without compensating for deviation and without compensating for temperature, took 1.5 of my 2/10 temperature away, or tolerance away. Plus my part was warm. So add that all together, and I ground those parts undersized, 2.5 to 3/10. So I was out of tolerance. Why? Again, not taking into account the temperature, not taking into account deviation, not taking into account the temperature of the part that came off the machine that perhaps was a little warm from grinding. So that's how important it is to make sure you use the deviation chart and you stabilize the temperature, make sure it gets down to ambient temperature so everything is the same. When you're working within a couple of tenths like that on larger parts. Now you're working with smaller parts, such as this one, it's still going to be important, but it's not, doesn't have the mass, so it's not going to grow as much. This part's going to grow much more because it has more mass. So pay attention when you're grinding within a couple of tenths. I don't care if it's flat grinding, cylindrical grinding, ID grinding. Pay attention to temperature and pay attention to the deviation chart. So thanks for watching.
Gauge blocks are one of the more unique measuring tools. Let me give you a little example here. Let's say we wanted to to build a stack of gauge blocks 1.5573 inches high. Okay, the way we go about doing it is we look at this rightmost digit in the number. You see that's a 3, and it's in the 1, 2, 3, 4th decimal place. That makes it 3/10,000ths of an inch. Well, we're not going to find a 3/10,000ths of an inch thick block in our set, so we have to go take the next best thing. If you remember, these first 10 blocks here are in 10,000th of an inch increments, plus 1/10. So we look for this block right here. I see we have a 0.1003 thick block. That's going to be our first block. Let's write it down, 0.1003. Do subtraction. 3 minus 3 is 0. You can see we got rid of that rightmost digit. 7 minus 0 is 7. 5 minus 0 is 5. 5 minus 1 is 4. That leaves us with 1.457 inches. Look at this right digit again. It's a 7. Okay, it's in the 1, 2, 3rd decimal place over. That makes it 7/1000ths of an inch. There are no 7/1000ths thick blocks in here, but there are 0.107s. Remember, all these center blocks here are 0.101 through 150. So there should be a 107 in there somewhere, right about here. Let's write that one down. 0.107. Do the math. 0, 0, 5, 3, 1. That leaves us with 1.350. Well, remember I said these middle blocks here are 50,000ths increments, so there should be a 350 in there somewhere, and sure enough, 350. Let's write that one down. 350. Subtract 0, 0, 0, 0. Leaves us with 1 inch. The upper blocks are 1 inch increments. Starting with 1 inch. Okay, so we got our 4 blocks. Hopefully we stack these up, we'll get 1.5573. Alright, how do we make a stack of gauge blocks? Well, first thing we do is clean all the grease off of them. I like to use alcohol. It's a little easier on your hands than petroleum solvents. So wipe all the grease off of them. As I said before, all my blocks are stored well greased so they don't corrode. All right, once you get them cleaned off, then what you do is you hold one in each hand and you wipe them off on your wrist. And what that does is it gets all the lint from the rag or any extra dirt or debris off of them, so you can ring them together. And the way you ring them is you put one block, corner of one block in the center of the other block, push them together, and you cross them and give them a little twist as you're pushing them together. And what that does, remember I said these are really super accurate blocks. They're accurate to within millionths of an inch, and they have flatness to boot. And what happens is when you ring them together like that, all the air is forced out from between them. So what you're left is air pressure all around them that holds them together, and they stick together. As a matter of fact, the better lab grade blocks, if you ring them together like this and leave them set overnight, the molecules will actually grow together and 2 blocks will become 1. Not a good thing for the gauge blocks, but it's kind of a cool concept. Alright, let's finish up here. Let's ring the next 2 together. Okay. Ring the last 2 together. Alright, that gives us a stack of gauge blocks. I always like to just check them with a pair of calipers as a little sanity check. See if my math is right. 1.557. Okay, we're going for 1.5573. I think I'd trust this over this. Okay, so that's one example. Let's clean up the board here and take a look at another example. It really needs some dry erase markers, I think. Alright. Suppose we wanted to build a stack of gauge blocks 1.5873 inches tall. All right, same as before, we'll look at this right digit. It's a 3/10,000ths place. So we'll use the 0.1003 block. That's this one right here. Write down 0.1003. Do the math. Leaves us with 1.487. Now there's always an exception to the rule. Okay, this time we're going to have to do it a little bit differently than last time. Remember I said these center blocks in through here are all in 50,000ths increments. That's 0.05. So if we look at this second decimal place here, when we choose the block to wipe out this 7, we have to keep an eye on the second place. We want to make this turn out to be either 0 or 5. 0 or 5, 50,000ths increment. Alright, so 107 won't work because 8 minus 0 is 8. That won't work. But let's see, what other blocks do we have that end in 7? 147, 8 minus 4 is 4. That won't work. How about 137? 137. 8 minus 3 is 5. There we go. Alright, let's write down 137. 137. Do the math. 0, 5, 3. 1.350. See, now our second decimal place here is a 5. So I think now we've done this before, right? We know what's going to happen. We're going to find a 350, which I already have out here. .350. Now we should have a whole bunch of zeros to work with, right? Leaves us with 1 inch. There's your 1 inch. We're good to go. Stack all those up, we'll get 1.5873. That's about all there is to gauge blocks. I mean, I picked 2 examples. These are the 2 issues you run into when you stack them up. The first one is pretty easy. This one has that little extra step you have to watch out for in the second decimal place. But other than that, that's pretty much all there is to it. I'm going to grease these babies up and put them back in their resting place. You guys get yourself a set of gauge blocks and give it a try.
Hello, Keith Rucker here at VintageMachinery.org. Guys, last week or so, I got a question from a viewer that was sent in to me that was trying to identify basically what this set right here was. He had found one, didn't know what it was, asked me if I knew what it was, and I said, well, yeah, I know what it was. In fact, I've got a set of those myself. And I went about explaining to him what all it was involved. He asked me if I would do a little video on how to use this because he was interested. And I said, you know what, that's a good idea. Something a little bit different, and but it is an interesting little set, and I thought we'd talk about it. So what is it? First off, this is made by the C.E. Johannesson Company, who was very well known for making gauge blocks. In fact, C.E. Johannesson was a person who invented the gauge blocks. I'm going to tell you a little bit about the history here in just a second. But this right here is what they called an accessory set for using with gauge blocks. And it enables you to do some pretty cool things, and that's what we're going to talk about here. But this is really what I want to talk more about, is this, what they call the accessory set. This one, again, is made by C.E. Johannesson. It's got a Swedish name on it. Doesn't really say when it would have been made, or I don't see any dates or anything like that on it. I will note that it does say in here that these are calibrated at 20 degrees Celsius or 68 degrees Fahrenheit, which is the standard temperature that a precision measurement room, a metrology lab or whatever is typically kept at, because these things are so sensitive that just the temperature of them can change the measurements on them. So ideally you would want to use them in a climate controlled room that's kept at 68 degrees Fahrenheit or 20 degrees Celsius. But what we've got in here, this set actually allows you to do several different things. So these here are basically some tools that are used to hold the gauge blocks. We got some little ends down here that you can stack on with the gauge block, and then we have this, which is basically allows you to use your gauge blocks as a height gauge. But let's start with just looking at this tool here, because this is really key to how you would have used these gauge blocks in practicality. So what I'm going to do is we're going to put together a little stack here and show you how that would have been used. So let's start out with just something kind of simple. So these tools here, and there's several of these in different lengths, but these are basically just to help hold a stack, to keep them together so they don't fall apart. Now, in theory, you should be able to ring these together. You kind of squeeze them together. The surfaces are so flat that they should stick together. Mine are not as flat as they probably should be. Some of them will ring, some of them won't. But in this case, let's just say we wanted to make a stack that was 1.5 inches. I'm going to do something really simple here. This one is a 1 inch one, this is a 1/2 inch. You put them together, it's 1.5 inches. So what you can do now is just take the stack, open that up a little bit more. We'll put the stack in the holder here. Open it up a little bit more. All right, we clamp them down together. And now I have a very precise standard here that's 1.5 inches wide. And just to verify that, I'm going to take my calipers. We'll come in here, and it's right on the money, 1.5 inches. You could use a micrometer to measure that. It'd be more accurate. I'm just using the dial calipers because it's easy to show. But let's say you just needed that as a reference. Now you've got that stack, and you can put in a lot of different gauge blocks in here to get a very precise stack. That's probably the simplest way to use it, but you can also use some of these special ends in here to do some even cooler things. So you got these ends here. There's actually several different versions of these, and if you look, they're round on the ends like such. So now what I can do with these is I can actually use this. Let's say you had a hole that needed to be exactly 1.9 inches in diameter that you were boring in something, and you needed a way to measure that with a super precise setup here. So, and I picked 1.9 because I've already got 1.5 inches. These, if you look on the end, you see it's 0.2. So each one of these is 2/10 of an inch thick, and to verify that, we'll just use our calipers, 2/10. So I'm going to take this stack apart. We're going to put these on either end. So we'll take this one, put it on the bottom. We'll take this one, put it on the top. Like such. Now I can go over to a hole and I can see if that fits. Now, probably what you would have done is you would have had multiple stacks. Usually when you're doing something precision like a bore like that, you would have tolerances. It would have to be within a range. So let's just say that we're at 1.9 inches plus 0 minus 5 or something like that, 5/10 or 5 thousandths or 5/10 thousandths or whatever. You come up with 2 stacks and you could check it with a go, no-go gauge. So basically, if one of them fit, it was a go. If it didn't fit, it was no-go. So you could then use this for, again, doing inspection work by setting up a couple of different stacks with different measurements in it. So anyway, that one's for doing an inside hole measurement, and you could just run it in there. Again, 2 stacks. You see if it fits or it doesn't fit. All right, next thing we're going to do is show how to turn this into a height gauge for making very precise height measurements. There's all kinds of height gauges that are adjustable, moving up and down, but this is a case where you wanted to have something that you really set up was super accurate using the gauge blocks as a reference. So you would do is use this stand here, and first thing we'll notice on here, it says 1.375. It tells us how high. Basically, this stand actually becomes a gauge block. Let's say I want to make put a scribe at 2 inches high. So I'm just going to get a calculator here to make this easier. I'm going to put in 2 inches, and I'm going to subtract out of that the 1.375 minus 1.375. That tells me I need to put 625 thousandths in there. So first thing I'm going to do is take my little holder here. There's just a little spring clip on the bottom. It goes in there. That height that I just told you, the 1.375, is from here to the top. We can start stacking our gauge blocks on top of that. So if I want to go to 2 inches, What I want to do is I want to really start out here on the end to get my measurements. I got 25 thousandths. So what I'm going to do is I'm going to grab a gauge block here. This is actually, again, the 25 thousandths is too thin for a gauge block. So this is 125 thousandths. So I'm going to subtract that out. Minus 0.125 equals ½ inch. So now I grab my ½ inch gauge block. And so when I put all these together inside over here, it's now 2 inches up to the top. So 2 inches from the plate up to the top. And I will finish by just putting in a little scribe here. The scribe, of course, is flush on the bottom, so the point down here on the end is going to be the same height as the top of the gauge block. We tighten it all down. And now I have a 2-inch stack for a height gauge, and then I can go over to another piece of work, and I'm not going to actually do it, but scribe a line on there if I'm doing a measurement, or if I need to just come in there even and measure across the top of something, I can sweep it and see if it's at least below that. You could again use 2 of these with a go no-go gauge. So you can make it where if it hits, one end is too tall or misses on the other one, you can then determine whether it was within a certain tolerance range. So again, another way you can use this. Set also has the center in here. This is a 60-degree center. So if you wanted to check a hole height or have something you could run between centers on the surface plate, you could put that in there. Basically, again, here, if you look, the center is even with flush with the top there. So now that center is at 2 inches above the surface plate. Another tool that's in here is this little scraper. This is a little triangular shaped 3-sided scraper. And basically what this is for is to just kind of come in here and scrape the top of your, not trying to remove metal, but a lot of times you would use grease on these gauge blocks to help them ring together. So you can basically just use this to real quickly get that surface cleaned off and flat again and at the proper height. So that is also included in the accessory kit. So there you go, just a little bit about the Johanneson gauge block accessory kit. And these are out there, you can find them. You see them come up for sale on eBay from time to time. I don't recall where I got mine. This may have actually been an eBay purchase at one point in time. It seems like I remember purchasing this off eBay. I may have got it at an auction or someplace else. I really don't remember. But they do come up. I wouldn't say they're super common, but if you look for them, they're out there. And probably by me doing this video, the price just went up on them. That seems like the way it usually works. But anyway, I had a viewer ask about it, how it was used. And guys, I am quite sure that there are probably many more ways that you can use this than what I just showed. But those are some of the ways that I know how to use it. And I have used this set for doing exactly the kind of stuff we just talked about. Well, there you go, guys. Just a little quick video on how to use the gauge block accessory kit and a little bit about gauge blocks in general. These are extremely handy tools to have in the shop, particularly the gauge block set. I use these a lot. Probably the biggest thing I use them for is when I'm setting up a sign plate. If I'm over on the grinder or something like that, and I can use a sign plate to get a very precise angle. I can calculate a stack that needs to go up underneath that, and I use the gauge blocks to set that sign plate with. But they have so many more uses, and particularly when you start getting down and doing super precision work to the 10,000th of an inch level, you need to have some of these just as references to use in the shop. Very critical to have that, and tool and die makers really rely on these quite a lot. Honestly, most of the work I do is probably not to the level of precision that I need these for, but every now and then jobs come in that you need them for. Really like them. I probably need to be on the lookout on a little bit newer set that's maybe in a little bit better shape, but again, for the work that I'm doing, these are more than accurate enough. So with that, that's going to be a wrap, guys. As always, thanks for watching. Please subscribe to the channel if you haven't already. Leave comments if you like, and we'll catch you on the next video.
Welcome to How To, a Quality Digest series for quality control, quality assurance specialists who need quick instruction on how to get something done. This episode is sponsored by Mitutoyo. And now Craig Howell of CPM Labs is going to show us how and why to use ceramic gauge blocks.
Great. This is a set of gauge blocks Mitutoyo provides specifically tailored for micrometers. You'll notice the different sizes. They're not 100, 200, 300, 400. They stagger the final digit so the anvil and spindle on a micrometer at different rotations. This will show up any lead error and show up any parallelism error all in one.
Okay.
Also comes with a optical flat, which also it's two-sided. It's also an optical parallel. So you can do that for the parallelism. That's critical on micrometer calibration. Gauge blocks are not enough. That's part of the equation, but there's more to it. There's flatness of the anvil. This is normally used under a monochromatic light, and it'll show up the different light bands for flatness. Each light band, each curvature of light band is 12 millionths of an inch. And then you would contact them together and count the light bands, and you could actually figure the parallelism from that.
And I should point out that there is a separate videos on how to calibrate a micrometer and also how to do your flatness and parallelism
Right.
using a monochromatic light source and the optical flat.
Right.
So different set of videos, search for them.
All right. So why would you bother with ceramic? There's a number of reasons they have. There are some definite advantages. They're much more abrasive resistant than steel. But
why do you have to worry about that?
Well, a lot of times the anvils and spindles are not quite as flat as you would like them to be, and they will have different. We always deburr micrometers before we start, but there still ends up being things that can scratch the gauge block or hurt it, damage it in some way. Ceramic has superior abrasion resistance. They're much better. They're about 10 times, 5 to 10 times the abrasion resistance of steel, and even 4 to 5 times that of carbide, which is the main reason people use carbide, is abrasion. The thermal expansion, the coefficient of expansion, how much these grow under heat conditions. Ceramic's a lot closer to steel than carbide is. Okay. So that would work. You can ring ceramic and steel gauge blocks together. You can put them together and ring. Ring is a process of getting them to where they will stick to each other.
Actually, can we, let me move this a little bit. If you can do that under the camera there,
Sure.
maybe we can see that, okay.
We'll try doing a ring process when they're both very, very clean. You don't want to have any dirt, or you're just grinding it right into the gauge block. You'll get to the point you can lift the bottom gauge block just with the contact of these two. They are rung together. So now you can get different lengths. Maybe you want to have a 2-inch or a 3-inch combined. Okay. You can combine ceramic with steel. So that's a definite advantage. The dimensions that are printed on the blocks, black on white, I tell you, out on the shop floor, especially with my eyes, sometimes trying to find the number, you got to keep rotating this back and forth.
Get the light reflect off it just right.
See, just right. This one, you have no doubt what block you're dealing with. These are fantastic. You have to be very careful. You don't want to drop them.
But are they, I mean, will they, I think ceramic plate, like I'm going to drop it and it's going to shatter into a million pieces.
Right, these are not that. These are very durable. They've made them to where they can survive the shock of being dropped. We don't recommend that. That's not a good practice, but if it happens, your 1-inch block you won't end up with 300 thousandths blocks. Okay. They will not shatter or break. They're non-magnetic is another advantage of ceramic. Steel gauge blocks can become magnetized. We have to demagnetize them occasionally when we calibrate. They can attract chips, metal, flakes. These won't attract anything. The grain structure is very, very tight and dense with ceramic, so they tend to ring better together. When you're ringing them together, they will ring a lot easier than steel ones will, and the ringing is a much tighter contact with each other. Now, when you ring gauge blocks together, it's always advisable at the end of the day to pull them apart.
Why is that?
If there was any sort, especially with steel gauge blocks, if there was any sort of contamination, they can oxidize, rust, a number of different things. If there's any coolant, that sort of thing. Also, dimensionally, I don't have the specifics, but I know NIST never recommends ringing if you don't have to. So surely don't leave them that way.
Okay. Oh man, if you
You can do it.
yeah,
But it takes quite a bit.
And actually, the thing that's weird. Wow, those are really. Only way to get them apart was to
slide them.
Was to slide them apart. Now, oh, I'm sorry. You said I could drop these.
Your head. Watch your head.
So, and also, so let me see if I can ring them together. Wow, that rung. I've never worked with ceramic gauge blocks. I've only played around with the steel ones. Boy, those just almost like snap together like Legos.
Just about. So that's why you would choose this specific set of blocks.
No, you touched on it, but I'd like you to discuss again why you should always use gloves when handling gauge blocks. I guess particularly maybe steel ones, but
Two major reasons. Mostly there would be heat transfer from your hands, and that we would normally in a lab use cotton gloves.
Okay.
But under the lights, I didn't figure heat transfer was going to really be too definite there. The other part is the oils in your skin. A lot of people have very abrasive. We'll find on our precision tools, and some of you have seen probably on your lathes and your mills, where people rest their hands, it'll actually rust in that area.
Okay.
Well, you get that on a different level. But with gauge blocks, Mitutoyo also provides an inspection report that shows all the different dimensions of these, so you know exactly how far off they are, the total variation on the block. Mitutoyo just does an excellent job with this sort of thing. So you can when you're at the point of actually applying these, you'll know exactly what they measured.
okay.
So there you have it. That is a Mitutoyo ceramic gauge block set up specifically for micrometers, but you can use it also on anything that you need different levels of checking within an inch.
Okay. All right. Well, thank you, Craig. And thanks to all of you for joining us. Obviously, thanks to Mitutoyo for sponsoring the show and providing the ceramic gauge blocks.
And now just a few more things about gauge blocks. Gauge blocks have been around for a long time, as you can see from this picture of a variety of old-style gauge blocks. Gauge blocks come in both metric and inch sets. You can see that the smallest size blocks for a metric set are in increments of 1 micron, and the smallest set of gauge blocks for the inch set are in 1/10,000th inch increments. The gauge block's key points are that they have a reference plane and measure plane. It's no longer a reference point and measure point. It's a reference plane and measure plane. Also, you'll notice that it doesn't matter which one you start with. You could flip the blocks over and have the opposite end be the reference plane and the end from it be the measure plane. That is why it's referred to as reversible reference surfaces. What's key about gauge blocks is that the line of measurement is any perpendicular surface, and the surface finish is critical for the gauge block. Using Johansson's patent, 11 blocks in 4 series can combine to form any dimension from 2 mm to 202 mm in steps of 1/1000th of a millimeter, or a micron. That's a total of 200,000 combinations. Key gauge block nomenclature. You have the long blocks, which are any blocks longer than 4 inches. Thin blocks are blocks in 1/10th of an inch or thinner series. And then you also have wear blocks that are reserved to be used as the reference surfaces, so that you don't wear the other blocks during use. These wear blocks can be changed out without having to worry about changing out all of the other incremental blocks. A group of blocks rung together is referred to as a stack. Another key feature of the gauge block that makes it so precise is the surface finish. Surface finish considerations for the gauge block are roughness, which is a finely spaced surface, irregularity, waviness, which is an irregular surface condition of greater spacing than roughness. And then you have various flaws, which are irregularities that do not appear in a consistent pattern, such as a dent, nick, or burr. The lay is the predominant direction of a surface pattern. The lay is the predominant direction of a surface pattern. To make a surface finish adequate for a gauge block, first, you have to machine the surface. In diagram A, we see that a crystalline metal surface that has been machined on a lathe can be visualized as having high peaks and deep valleys. Certainly, not good enough yet to be used as a gauge block. In diagram B, you go through the grinding process, which reduces the high peaks, but produces new and smaller peaks and valleys, the dimensions of which depend on the grit size. In diagram C, we go to honing. In honing, due to the fineness of the cutting grits and irregularity of the cutting motion, it reduces a surface to one of just a variety of fine scratches. But still, it's not adequate for a gauge block. The next process is lapping. Lapping normally leaves a finish of minute scratches. The scratch pitch is finer than that left by a hone. Gauge block surfaces have a high degree of flatness, as well as surface finish. Only occasional, extremely shallow scratches are left that won't affect the dimension. However, if you try to fix a surface by buffing it, you can actually destroy that flatness. Buffing produces sufficient heat to bring about a plastic flow, and while aiding the reflectability, it will reduce the quality of the surface flatness. That means it'll look great, but it'll be much worse as far as its functional use. Gauge blocks come in a variety of grades, from calibration grade to work grade. These are charts that describe the tolerances for each of those grades. How do you calibrate a gauge block? What is calibration? It's a verification of the block is within a tolerance specified. How is it done? By comparison to a master standard of known calibration and known traceability to a national length standard in America, which is NIST. When is it done? Periodically, according to a systematic program based on statistical quality control. It's done not less often than annually for grade AA, quarterly for grade A, and semi-annually for grade B, when required by visual inspection, ringability decline, or slipping quality control level. Who calibrates the working sets? The user's gauge department, or any facilities for calibrating master sets, may have the capacity to calibrate working sets. Who calibrates the master sets? Those are sent out to independent metrology laboratories or manufacturers of gauge blocks, and they are traceable to NIST. What is done with a gauge block that is too worn to be used? It's replaced. You can't adjust it. You can't fix it. It has to be replaced. What happens when you have an entirely worn set? They may be regarded for a lower level of precision. For example, a AA set may end up being a B set. Gauge blocks provide an accepted method of calibration of measurement methods. But ask the question, could this measurement be made using the gauge block directly instead of through this middleman? In order to do so, you need to use the gauge block accessory set seen in the previous video that allows us to measure with the gauge blocks directly. Here's a variety of accessories put together to allow you to use square gauge blocks to measure directly. These sets have end standards. Why do they have end standards? Because the gauge blocks themselves cannot always fit into gaps or other characteristics. Standards are used in addition to the gauge blocks in order to generate the measurement. Here's a variety of end standards chosen for each particular application. What is the benefit of using the gauge blocks directly? The advantage of gauge blocks for attribute gauging. In situation A, you have a tolerance of plus or minus 5 thousandths or a total of 10 thousandths. So, in order to set the snap gauge, it has to be set to 1/10 of the tolerance or 1 thousandths. Its setting gauge has to be 1/10 of the snap gauge, so it has to be 1/10. The gauge blocks have to be 10:1 to the setting gauge. So now they're at 10 millions. And the master blocks, to set the gauge blocks, has to be 1/10 of that. So, it has to be at 1 millionth. Now if you drop down your tolerance to plus or minus 1 thousandths and you have to go 10:1 to that, to your snap gauge, now you're at 2/10 on the snap gauge. Your setting gauge has to be 20 millionths. Your gauge blocks have to be 2 millionths, but your gauge, your master blocks are only 1/1,000,000th, and that's not 10 to 1. So now you run into a problem. But if you jump over to D, you have a tolerance of plus or minus 1/10, which is a total of 2/10, but the gauge blocks are good to 20 millions and the master blocks are good to 2 millions. So you see, if you use the gauge blocks directly without all of the additional steps, you don't have that loss that you need for the resolution of the gauges in between. Rules for gauge block care. Never attempt to ring or otherwise use gauge blocks that have been in contact with chips, dust, or dirt-laden cutting fluids. Before using, clean gauge blocks with a high-grade solvent or a commercial gauge block cleaner. Wipe dry with a lint-free tissue. Do not allow blocks to remain wrung together for long periods, separate daily. If you don't do so, they will become difficult to separate. Steel gauge blocks may even corrode together and become permanently wrung together when not in use. Place blocks in a safe place where they will not be damaged, preferably in their case. Before putting blocks away, clean the blocks and cover with a non-corrosive oil, grease, or commercial preservative. Be on constant guard for burrs. If anything has been placed on a block, or if it does not ring readily, use a conditioning stone immediately. Thoroughly clean the gauge block case periodically. Putting a clean block into a dirty case doesn't help you at all. The conditioning stone is one of your best allies to ensure reliable measurements and long life from gauge blocks. They are used to remove fine burrs from the edges of the gauge block. The blocks are firmly wrung along its smooth, crystalline surface to remove burrs and nicks without abrading or changing the flatness of the surface. You can see a variety of conditions will actually generate error when using gauge blocks. These are all conditions you need to avoid, except for the properly wrung gauge blocks. Also, you have to be very careful when using gauge blocks with materials other than steel, because gauge blocks made of steel at different temperatures than standard will expand at the same rate as steel, but will not expand at the same rate of other materials such as aluminum, zinc, or even tungsten carbide. That's why it's important to measure at a specific temperature to avoid those errors, as seen in the previous video. That's it for gauge blocks. You'll have an opportunity to use them later in the lab.